morning, dear colleagues. My name is Punanov. I present a work carried out by researchers and engineers from Institute of Electrophysics in collaboration with the Institute Research and Development Institute of Machine Engineering. My work is devoted to development of high voltage compact pulsed plasma thruster utilizing liquid propellant. In my talk I will present the preliminary results which we obtained during the tests of the developed prototype. What is the motivation for this work is that small satellites require small thrusters for orbit correction. These thrusters have to be compact, light and effective in the meaning of not to consume too much material of the propellant. Because the material is limited on the orbit as opposed to energy, which is practically unlimited. The good scheme for that is to accelerate propellant with as high velocity as possible. And the good option for this is to use pulsed plasma thrusters, which provide relatively high velocity of plasma flow. The problem is that existing plasma thrusters based on capacitors, they are too heavy for microsatellites. And what can we do about this? We can reduce the mass of energy storage by the expense of the value of stored energy and compensate it by increasing of operating frequency. And what particular design we propose? At first, we propose to use inductive storage instead of capacitor, because inductive storage has higher energy density at the output stage of the device to be compared to capacitors. And the second point is that we propose to use high operation mode of the pulse application. The third point is to use ceramics, particularly ferroelectric ceramics. This is because it can provide us the possibility to increase the share of ions at the initial stage of the breakdown. At the initial stage of the breakdown, the bias current is dominated over conduction current, so and it depends on permittivity. So we propose to use strontium type titanate capacitor ceramics, which is affordable and have high permittivity. And the last but not least point of this proposal is to use liquid dielectrics as propellant. This gives us an advantage to use a common propellant tank for all the directions. For example, 4 or more discharge units. And in our design, we propose to use vacuum and castor oils because also they are affordable and they have low pressures of saturated vapor. What we propose in particular, according to the these ideas, we developed a thruster which contains three main parts. The power unit, the pulse transformer, and the discharge unit. The power unit is needed for autonomous power supply of the device. Why do we need autonomous power supply? We have to measure very weak impulses, and any wires may distort the measurement. So we made a metal cylinder with transparent window, in which the cylinder contains a stack of batteries and an electronic circuit board. Electronic board is a controller for switching from the outside of the vacuum chamber. How it works? We irradiate the IR receiver with infrared light emission diode, and the signal is transmitted to a controller which control MOSFET switches. In this work we use only one of them. The second switch is for valve for dispensing of liquid propellant. This is the topic of our next work. And the pulse transformer generates the pulses of about 20 kilovolts, as it can be seen from this waveform. These waveforms were obtained while the transformer was loaded on different resistors. And the main load of the transformer is discharge unit. By the way, these waveforms were obtained in statical mode because we have to connect voltage divider and shunt to the oscilloscope, and we can help but use the cables. The main part of this thruster is, of course, the discharge unit. It consists of a coaxial ring anode and a rod-shaped cathode. The housing of the unit is made of polyamide. The substrate for the discharge is made out of capacitor ceramics. And for comparison with our previous results, we used another discharge unit with Teflon as propellant. This discharge unit have, as you see, similar geometry. The substrate have a channel for liquid propellant supply, which is supplied from the valve, but as I said, we did not use this mode in this work. For testing of liquid, by the way, we used dry ceramics for tests of in our tests for thrust measurements. Only for comparison, the results with Teflon and with wet ceramics. And the real tests were using liquids, castor and vacuum oil, as I said. And in this simple case, we just spread the oils on the surface of the discharge unit before the chamber was vacuumed. This small amount of liquid is enough to measure the thrust and to see that to see the difference as opposed to dry ceramics. This photo demonstrate the actual work of the thruster. All the main parts of the thruster were mounted on the platform, which was suspended in the chamber by a thin metal thread with a mirror mounted on this thread for measurements of angle of the rotation. The mass, the weight of this assembly without power unit is about half of a kilogram. Let's see what we have as a results. We measured the voltage and current in two cases. The first one is using of Teflon as propellant, and the second one is the using of ceramics. In case of Teflon, we see the distinct breakdown, the rapid drop of the voltage, and in case of ceramics, we don't see distinct breakdown. Despite this unusual behavior, ceramics demonstrate higher thrust than usually used Teflon. A few words about thrust measurements. This is our vacuum chamber. We use simple laser, transparent ruler, and a mirror to measure the angle, to measure the thrust. We've calculated the thrust using this formula, and for doing this we have to know some constants, which are moment of inertia of the rotating platform, period of its oscillations, distance from the mirror to the ruler, and the distance from the center of the discharge unit to the axis of the rotation, meaning the thread. And the actually measured value is the shift of the light beam on the transparent ruler, this X. The results. This table demonstrates that dry ceramics perform better than Teflon, and wet ceramics perform even better than dry ceramics. Despite the fact that it seemed to be that Teflon demonstrate high efficiency, energy efficiency, it doesn't matter for us because, as I said, we don't have to save energy, but we have to save the propellant on the orbit. And to sum up, the first point is that we developed an approach to get satisfactory thrust parameters using compact, high voltage, high repetition rate thruster utilizing liquid propellant. The second is that the results obtained in case of ferroelectric ceramics demonstrates higher thrust than in case of Teflon. Promising results with these oils open the way to future experiments with water as a liquid propellant. Of course, for this we have to finish our work on valve and the work on synchronization of this power liquid propellant supply system with discharge processes. This is all. Thank you for your attention, and I'm ready to answer the questions.